Ready for the next one? After we listen for like 10 more seconds. Okay, get out of here. I was pushing the wrong button. Okay, continuing along. So there are several different ways that we can think about our reaction rates. And so I'm going to talk about all three of those here briefly. So one is the average rate, which is the change in concentration of reactant or product over a specific time interval. So I showed you this picture before already, but now let's dissect this a little bit more. Okay. So for example, if we look at this average rate, perhaps between 5 and 10 seconds, okay, we would need to get the concentration at 5 seconds. So there it is, okay. And then we would get the concentration at 10 seconds. So perhaps, microseconds. So perhaps we were somehow able to take a data point every 5 microseconds. So that's what you can kind of see with these reaction profiles. And that could be done with spectroscopy the same way you did in lab with the equilibrium reactions, which is pretty much the preferred method for kinetics, is to use spectroscopy. So what we would then find over this average rate is we've got some delta NO, right, corresponding to that concentration. And then we've got some delta T. And then we could compute those numbers and get some average rate. And that's going to be in units. Here, this is going to be in units of molarity per microsecond, just because of the time base. But our rates are always going to be molarity over time. So the standard is molarity per second, but it doesn't have to be. So we could do molarity per microsecond in the case of a fast reaction. In the case of a very slow reaction, we could do molarity per day or molarity per hour or even molarity per year for a very, very slow reaction. So it's basically molarity per time for the rate. Okay. So the problem with this average rate, though, is the following. So suppose now we wanted to look at the average rate between 20 and 25 microseconds. Well, hopefully what you can tell from this graph is that is going to be a different value than between the 5 and 10 seconds, okay, microseconds, right? And we can tell because if we look at a slope right here, the slope here is much steeper than it is here. The slope gets more shallow as the reaction proceeds. So average rate isn't necessarily the best overall rate to use because it will depend on where we're at in the reaction. So we have something called instantaneous rate, and that's for you calculus lovers. Okay, so that would be the derivative of concentration as a function of time. Again, we're not holding you to that level of responsibility. But if we were to look at the instantaneous rate, it's very similar to the average rate. So we pick some time interval. But now what we do is look at the slope. So in other words, the tangent line, right, of some particular data point. And I'm going to try to do a really careful job drawing that. So that slope of NO2 from that tangent line would represent my rate. But also the problem with instantaneous rate that you might note is over this time interval, the instantaneous rate would be much different than perhaps over this time interval, right? If I draw a tangent line right there. So it's the same issue as the average rate, okay? And of course, we could also finally talk about the initial rate. And the initial rate is pretty much identical to the instantaneous rate, except for the initial rate is the slope at the very first data point, okay? And once again, you can see all of these things will be different, right? This initial rate has a much different slope than these two particular instantaneous rates. So none of these will work, unfortunately. We could certainly do all these. We could calculate initial rates and average rates and instantaneous rates. But because they're going to be different across the whole time series, we need a better metric, or we need a different way to quantify our reaction rates. Okay. And just one quick note, the initial rate is, out of all three of those, so the initial rate, instantaneous rate, and the average rate, the initial rate is used the most out of all those three, if there's any one of them that is going to be used. And the reason for that is because of these reversible reactions. So if we do have an equilibrium reaction, which you are all very familiar with now, we know that there's a reverse reaction. And that reversible reaction is important when the products have had time to build in concentration. That means later on in the reaction. So at maybe after the reaction has gone for a few minutes or hours or seconds or whatever. So typically, reaction rates are studied at very small concentrations and immediately after products and reactants are mixed. That gives us the initial rate. And this is important because when the reverse reaction hasn't had time to build in concentration, it makes it much easier for us to study the rate of reaction kind of near the beginning. But all the same, initial rate, average rate, instantaneous rate, they're not perfect because they're not consistent throughout an entire reaction time. So what we need is a rate constant, and that's coming next.